Okay, so I just asked in chat, now that I'm live and my microphone seems to be working and everything, I just asked in chat 1 to 5 how we feel about the quiz, getting the quiz to work. Not the quiz's content, but getting used to the way that everything works, the Proctorio and everything. So what's going to happen? I know you all are anxious about the test and everything. So let me say a couple things about that. The test, did I put that? Reminder, the test is next Friday. The cutoff for new material will be on Monday after Monday's class. Well, after the quiz on Wednesday, but that will be the cutoff for new material. Everything that I talk about in class Wednesday and stream will be for the next test. Also, there have been some issues with people getting on the getting things uploaded for problem sets. I'm going to change the way that problem sets are uploaded. The notes are uploaded. What you're going to do is upload one set of notes for each class. That way it's easier to grade, and they'll just be 5 points each. And I will set that up starting as soon as I get a moment to set it up, probably tomorrow. Are there any questions before we get started? Please type them. Also, TA's here. Everyone say hi. Mike, don't say hi. That's going to spam the chat. You know. Okay, some of you can spam the chat. Yes, there will be a study guide for test 3. I haven't made it yet. And yes, my office hours are still the same. And do the notes need to be of a certain length? They need to be sufficient to have highlight of the information. Will the problem set simply scored into Gradescope? Yes. Gradescope, I'm just going to, what I'm going to do is instead of having one assignment for both, I'm going to have 2 assignments. So it'll be notes this day, notes that day, notes of that lecture, notes of that, notes of that, notes of that, notes of that. So there'll be 2 assignments per week instead of 1 for notes, and it'll just be easier on everybody if there's only one. If there's only one day associated with each one. Any other questions? Okay. So yes, you will get a study guide for a thing. Oh, calculators. I've had it with the Proctorio. You're going to be able to use scientific calculators, and they can even do calculus, and they can even do combinatorics, and I will be fine with it. There will be an instruction to hold up your calculator to the camera when you start Proctorio, and I need to add a note for that. Add instruction for holding up calculator. For holding up calculator. There will also be instructions to say keep your calculator on the desk and don't put it in your lap, because if you put it in your lap out of the sight of the Proctorio, it's going to flag you. Can you use the calculator on the computer? I may allow you to use some apps, but not others, and those will be restricted to Windows. The reason why is because some of the calculators on a computer have the algorithm to do modulo arithmetic for big numbers. And that's one of the things I want you to figure out how to do on the test. So probably not. You'll probably be restricted to handheld calculators that will choke if you try to do modulo arithmetic with big numbers without figuring out how to do them. Or the calculator in Proctorio itself. Because there's just no other way to do it. So I'm giving up on the using the Proctorio calculator, which would be the ideal solution, and I'm just trusting you to use the same calculator the whole time and not stick it in your lap and then use a different calculator. So, you know, so let me talk about real fast about what Proctorio does. Proctorio flags for review. Okay, it doesn't flag. It doesn't say you failed, right? It doesn't say you cheated. It says this. The algorithm says this is suspicious. Would you review it? So what happens is that then me, TA, somebody else has to go in and visually review it. So we watch the video of you doing it, and it streams by really fast. A couple things about that. So there is a live person at the other end of that camera. Please put your shirts on. Please. Also, It's not just an algorithm. There's actually, it flags for review. So the computer itself cannot, does not accuse you of cheating, okay? If I think there's something suspicious, I'm going to contact you. And we're going to talk about it. And then we're going to talk about it some more. I'm not going to allow the system to say you cheated, right? If someone says you cheated, it's going to be me. So if it flags, it just means I have to go review the video, and it takes like 2 seconds per flag. And there's going to be things that is flagged for everybody at certain times. So I want to talk about that because of the way we're doing this. What I want is that everybody needs to have Discord open during the test. And I'll get you testing procedures when they come. I don't have them all yet. And I know you all are nervous about the test. But when testing procedures come, one of the procedures will probably be on Discord. The reason for that is, and yes, and I'll make an exception for Discord in the thing. I don't know 100% how this is going to work, but if someone has an issue with Factorio, it may not be that you have to be on Discord. It may just be that you have Discord available so that if, heaven forbid, you do have an issue, you have to do that. Now, answer sheet for the test. That is for calculus. Okay? So your test is going to be entirely online like it currently is. I toyed with the idea of making you show a bunch of your work, and in the end, I just went... I may have you have a blank sheet of paper. You hold up the blank sheet of paper to the camera at the end to say that you actually did work and you weren't cheating. That procedure may happen, but an actual answer sheet which you upload to the system, it's for calculus we have to do it. For you guys, I already did most of the stuff for which I really wanted you to show your work. And because of that, it's going to be, I think I can get away with just doing the online thing. Now, if you want to show your work for partial credit, we'll get into that. I haven't completely worked out that system yet. But if you want to show your work for partial credit, there probably will be a way. I just haven't figured it out yet. So there will be no test. There will be no answer sheet. Please have blank paper so that you can, if you can have scratch paper. Okay. So, does anyone else have any questions, comments, issues, suggestions, thoughts? Okay. So. Yes. So at the beginning of the thing, the way it'll be set up is that you'll have so for some things you're going to have to type answers, for others you won't. The exact nature of those things I have to work out. And then, SDS has basically told us apparently that we can give extra time and then everything else is up to us. I don't know what's going on, and no, I have not posted the WebAssign yet, but there will be WebAssign. Hopefully that will go up tonight. If it doesn't go up tonight, then it'll be due probably some other time. Will the test answers be auto-graded? Likely most of them will, with the caveat that the test will be, with the caveat that you could show work. And again, I haven't worked out everything about that yet, but it will be involved in somehow. Yes, questions could have multiple answers. There probably will be like an essay field for some of them where they have to be graded by hand. So if that answers your question. So the auto grading, some things will be, some things won't be. There'll be a little multiple choice. That'll be auto graded. There'll be a little true false. That'll be auto graded. Everything else, we're going to have different things. And again, you can contest an auto grade. Hey, I typed in that thing wrong. Okay, that's fine. We'll go back and we'll fix it. I know that's a little stressful, but that's how it's got to be. The test will be at Friday, not this Friday, next Friday at 9:30. You have to be there at the start of the test. Think of it just like you were coming to the auditorium. Okay, So the test is going to go live at a certain time. It's going to go dead at a certain time. It's not going to be like a timer where, I give you so much time to take the test. As a matter of fact, the timer's going to lie, okay? Because what I want is the thing to be due at a certain time, okay? And then what I'll do is when I do all that, that's how the test is going to be. It's going to open at a time, close at a time. Are there any other questions? And for those of you with SDS, I'm going to figure out how to give you extra time later. So we're ditching the whole scan thing for discrete. Calculus, different story. So for discrete, no scanning involved. You may have to show up your paper like this if you want to get partial credit for work. Any other questions? Okay. So I've spent the last 11 minutes talking about the test and 0 minutes talking about what we want to go over today. So let's go over the quiz. Also, check this out, guys. Let me see if it's up. So I have a plan. I plan to write on this and have it appear there. I have a backup plan, which is to write on this and stream from this. Okay? I have a backup plan, which is to stream from this. I have a backup plan, which is to use the DocuCam. And if you don't think that's cool, DocuCam. Check that out. I need to make the thing bigger so that it shows my actual arm when I'm writing. I haven't gotten that. So I have plan, backup plan, backup plan. The only thing I don't have a plan for right now is if my internet goes down. I'm going to talk to my neighbor tomorrow to see if we can be each other's backup because I think he's on Spectrum, not Spectrum. Yeah, whichever one the cable company is now, and I'm on whichever one whatever Verizon became. So I've got FiOS, and I think the person next door has cable. That. Extended time, yes. So Michael can arrange that. I'll arrange that. We'll do extended time for SDS. I don't know about the other accommodations yet. I don't know about, and SDS has basically gone, yeah, I'm not hearing, and it's being very annoying. So I don't know what SDS's plans are, except that they've said, it's your problem now. We'll yell at you later if you don't do it right. Anyway, glory, hallelujah. Let's go ahead and let's talk about the quiz since now I've gone for 13 minutes. Okay, so here's the quiz rubric. Oh, no, go back. The best way to get at this, you can break it up differently, but the best way to do this is to know that the 30th is going to be 1 by Fermat's theorem. So I use Fermat's theorem to get that result. And then using that result, I get, I just work it out. Did everyone get 1? 1 to 5, how do we feel about that one? 1 to 5, how do we feel about number 1? There we go. There we go. I think we got some lag there. Okay. Now for number 2, it's basically the same story, right? Well, I'm sorry, completely different story. For number 2, the answer is the same. So for number 2, I put in A5. This is the explicit formula for the thing. So I put in 5, and then I do 10 minus 5. I get 5 over 5, and I get 1. Okay, 1 to 5, how do we feel about that one? Okay. All right. Yeah. And then the next one is just a recursive sequence. So when here, I don't know why it's blurry. It's not that blurry on this other one. That's so annoying. Here, S0 equals 1. Let's see if I can fix the blurry. Right? And then, so I sub in for S1, and I get, so I sub in S0 here, which is 2. Yeah, so now I'm talking about question 3. Sorry if I messed that up. So um, so ha ha ha. So the S1 equals 2 times 1 plus 5 equals 7. And then I do S3, S2 there, and everyone sees that. And then I do S3. How do we feel about that? 1 to 5. I'm sorry. S2 equals 1 times 4 plus 5. Where are you seeing something incorrect here? So apparently people are upset about this. It's entirely possible that I messed it up. Oh, I didn't. So this is 2 times 7, right? So this value subs in there. This value subs in there, right? And then this value subs in there. So S3 equals 2 times 19 plus 5. Okay. All right. So that's how that works. Are there any questions? Comments, issues, suggestions, thoughts. And then one thing you found memorable from the last lecture. Probably that nothing worked. Okay. Also, I did figure out a way to do makeups. I just haven't implemented that yet. So I did test it, but I haven't implemented makeups. And I forgot to announce that in calculus. I need to tell people. But I did figure out a way to do that. Hopefully that's up on Friday. Any questions? That will involve scanning with a paper quiz. That will involve more complicated procedures. But I did figure out how to do it. Proctored makeups. Any other questions, comments, issues, suggestions, thoughts? Okay. So let's talk about what we wanted to talk about today. So let's talk about where the rest of the course is going. So I said I was going to stick to this textbook, and yeah, no. I'm trying, but the textbook, it's not that it stinks, it's just written for a different audience, okay? The textbook is written for comp sci people and not IT people. So I can't do, there's so much stuff in here that we just don't care about, okay? So while we're going to stick kind of to the textbook, we're just going to be like, I'm skipping this part, I'm skipping this part, I'm skipping this part, I'm skipping this part, okay? The textbook doesn't stink. The textbook is very good for what it's meant to be. Okay, fine. The textbook stinks. So I don't know if I'm teaching this again next semester. I'm not scheduled to. They wanted me to teach it, but they also wanted me to teach 2 sections of pre-calc as well, and I can't do 3 math lectures. So I may be doing. Right now, I'm scheduled to do 2 sections of pre-calc and 1 section of calc. I don't know what goes on the following semester. And they may, in the end, just take me out of calculus and say, no, we need you to teach this. They want me to teach this again, but I can't do 3 math lectures. That's just not doable. So anyway, I don't know what the textbook will be next year, but it probably won't be this one. Anyway, totally irrelevant to anything that you want to know about. Our big overriding goals, okay? So let's do the cool stuff. The big overriding goal. I want to write recursive functions. Now, we mostly ditched this because we're not writing functions. I talked about recursion last time. I showed you one. I'll do that again, not this time. It'll probably be later when I do one of the other topics, which is later on the list. And I want to show that there's stuff I cannot do. I want to show that there's stuff I can't compute. I want to show there's stuff I can't even prove. And I want to show that there's stuff I can't even throw in a loop. And we're actually going to do this the other way. We're going to prove this first, then probably this, and then this. This right here is a major theorem. It's called Gödel's theorem. And it's big. And I want to do it. It'll probably be one of the last things I do. And it's really cool and really big and really important. It's like one of those things that philosophy people like to talk about, right? Oh, there's stuff you can't even prove, you know? Okay. And I want to talk about complexity classes. I want to get into P versus NP because that's important for IT people to understand. And then, so to do all this stuff, basically what I'm going to skip, and get in the cool stuff. Now, the summation stuff I'm going to mention. I've seen summation notation already from a bunch of you. I'm kind of happy with the way it is, and then I'm just going to ditch the rest of it. And then we're going to skip shallow induction. It's just foreplay. Let's go for the real thing. Not that there's nothing wrong with foreplay, but in this class, we've got other foreplay that we're going to do. We're not going to do this. This is just too much. And we're going to do the cool stuff. We're going to start with deep induction. Shallow induction is what you use to prove a bunch of formulas that we don't care about. We're also skipping all of the stuff about like forming the where we solve for the series, where we take a recursive series or sequence and try to solve for the explicit formula. We're not going to do that. It's boring, and who cares? Computers do that for you. So we're going to skip that stuff because who cares? You may need it in a programming class later, and I'll just leave it to the programming person to yell at you about not knowing it, and then they can yell at me. But you probably won't. Any questions, comments, issues, suggestions, thoughts? Okay. All right, so that's the plan. Let's talk about. So last time we talked about what sequences were, and sequences come up at 5.1, and then I did recursion, which is in 5.6, recursively defined sequences. I actually did mostly this. Today what we're going to talk about is what is a series and what does it mean. That's, kind of the summation rules. We're not going to spend much time on it if you just need to see it. And you need the connection between a series and a sequence. All you have to remember is a series is just a sequence with sums involved. And then what we're going to talk about is sequencing sets. So what we want to do is we want to run, why do we care about sequences? Well, we want to run for each loops, right? So in order to run a for each loop against a set, there has to be a way to do 1, 2, 3, 4. So there has to be a way to enumerate the items. That's actually a better way of saying it. Sequencing, better set enumeration. And then if there's time, we're going to get into the big thing, which is that there are things that are bigger than just normal infinity. Yeah, man, you're going to have a bigger infinity. So we'll talk about the set of we'll talk about the cardinality of a set. We talked about the cardinality of a set at the very beginning in Module 1 when we talked about the size of a set. Well, now we're going to have things that are bigger than infinity. And we're going to talk about what that means. Okay? Any questions, comments, issues, suggestions, thoughts? Anybody already clipping stuff to get me in trouble? Okay. Yes, bigger than infinity. Okay. So, that should so be a meme on the math thing, by the way. I love that. The bigger than infinity. Put text under it. Bigger than infinity and post it. Okay? That should be the meme for today. All right. Let's talk about these things. Let's talk about series. Not hearing Twitch. I don't understand that. Okay. So let's talk about series, and let's talk about this. So last time we had a sum. And a sum looks like this. I'm sorry, a sequence. And a sequence looks like this. So I've got Sn equals, I've got S naught equals 1. And I've got S1 equals Sn equals let's do Sn minus 1 plus 1. Boring. Okay, so what's the sequence going to be? This is actually the sequence of the natural numbers, right? I got 1, 2, 3, 4, 5, 6, 7, 8, 9. Everyone on board with that? 1 to 5, how do we feel about that? There we go. Okay, so I've got the set of, this is a boring sequence, right? S0 equals 1, S1 equals 2, S3 equals 3, etc., etc., etc. Now, what happens if I do this? What happens instead if I write a new series? And my new series I'll call AN. And AN is going to be the following. It's going to be AN equals 1. Everyone's on board with this series. Now, let's do a different one. Let's do AN equals S0 plus S1 plus S2 plus ... plus Sn. Okay? And the idea here is that I can do what's called a sum. Okay? So this particular thing, I'm going to abbreviate this, right? So I've got n terms and I'm going to rewrite that as this. Okay? So what I've done is I've taken the series, right? So this means right here that if n equals 2, I'm going to take Si, I'm going to add these two things together. And that's all the notation means. All right? So 1 to 5, how do we feel about summation notation? S2 equals, yes. So 1 to 5, how do we feel about this summation notation? There we go. Yeah. So you've probably seen it before, and if you have, that's good. Okay? Now, this is right here. If I have this, what I'm doing is I'm adding up all of the terms here. Okay? So if I have this is what's known as a series. And a series is some kind of summation of sums. And that's all it is. It's an infinite list of sums. So to give you the classic example, let's take this one. Sn equals 1 over n. Okay? And now I want the sum okay, not 1 over n, 1 over 2 to the n. Right? In other words, okay. Yes. So I'm winding up. I noticed that there's a large amount of latency in this stream. That happened last time, and it doesn't happen in the morning. So I think it's something to do with the amount of traffic heading to Twitch. If it keeps up, I'm going to try YouTube next if it keeps doing this. But that happened last time, and it also happened to the board last time, which has to go to Microsoft servers and then come back. I ordered better internet, so I ordered a full gigabit connection over. I ordered a full gigabit connection from Verizon or whatever it is, but that won't be here until next Thursday. They're doing a deal where if you're a teacher or a student, and I think it's just everybody now, you can get free installation. So, and they have to come and upgrade all my cable in the wall to fiber. So that's going to be fun, which is nice. So here's the example. This is called an infinite number of mathematicians walks into a bar. And that's all I ever want to say. Okay, this particular series equals 2. If you care, it converges. I don't. This is a Calc 2 thing. If you're interested in series, go take Calc 1, then go take Calc 2. You will have all you ever wanted to know about series. And that's the end of that. Any questions? Okay. Why did I mention it? Because it's one of those words that you run across. But the important thing to remember is that when you're dealing with the difference between a series and a sequence is one is just a sum. Okay? Series means sum. Okay? And it's actually a sum of it's actually a sequence of sums of another sequence. So anyway, the that's the whole point. And no, they aren't socially responsible because they're not keeping 6 feet away. So the summation notation, what it means is that what I'm going to do is I'm going to write a formula. And the formula is going to be to take 0 and do n. We've already seen one, okay? So remember that the binomial theorem. I can't spell. Here's another example. Okay? It said that x plus y to the n, or let's do a plus b to the n, equals a to the, so n choose 0, a to the n, b to the 0 plus n choose 1, a to the n minus 1, b to the first plus dot 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 plus n choose n, a to the 0, b to the n. Okay? There we go. So we've already seen this. This was the binomial theorem, and I can write that as this. If I want a simpler way to write it, I can write okay? So that's the summation form of it, all right? So with the summation form, it's just a way to write these things down quickly, okay? And with the summation form, what I've done is I'm taking this number here, this k, right? And then I'm adding it. So the way that I do this formally is the thing. I'm going to take k when k equals 0, right? I've got n choose 0, a to the n minus 0, b to the 0, plus, and then k equals 1, and I'm looping. And when I do my loop, I'm adding. So it's just a nice way of writing basically a loop with summation at the end of the thing. All right, so when k equals 2, k equals 3, and so on and so forth. Then I wind up with the last term. Backwards. One to five, how do we feel about that? Okay. And if you want more help, I'll put some practice exercises on the thing. Excuse me. But I don't really want to spend a lot of time on it. It's there. It's nice. We see it. It's nice. Now let's move on with our lives. Okay. And if you want me to come back to it, I will be happy to do more examples. I'll put one on the quiz for next time. And it's just a way of writing that loop so that the notation is tight. All right. Let's talk about the next thing I wanted to talk about. I'll bring it back. The next thing I wanted to talk about here, I talked about series and I talked about summation notation, and that's all I want to spend on it for class. If you want more time, I'll do it. Let's talk about enumerating sets. Okay? So recall that sets are unordered things. So, for example, okay, for example, oops, I have to put on the geeky glove. I'm doing the thing. So, for example, I can have the set that's an apple, an orange, and a pear. Okay? Now, that's the exact same thing as saying pear, orange, apple. These things have no intrinsic order. How do we feel about that 1 to 5, that these things have no intrinsic order? Right? This set here is the exact same set as the set orange, apple, pear. I don't care about the order. Order does not matter. Okay? All right. So this begs the question. Okay? What exactly? I want to go do a for each loop over this. Okay? So what's the computer need to do? If I want to run a loop over something, I want to create an algorithm to run over this thing. What does it need to do? It needs to assign something with order to these numbers. Okay? So what does the computer do? Okay? The computer assigns some number. Okay? The computer is going to say, okay, I'm going to associate 1 with the thing apple. I'm going to associate the thing 2 with orange. And I'm going to associate the number 3 with pear. Okay? Because the natural numbers, right? Now, an array is a little bit of a different thing, okay? An array already has order, right? So I make an array, but I have to be careful not to count anything twice, right? And that's essentially what you're doing when you make an array. That's what an array does. It's got indices that always start at 0. As a matter of fact, it's a computer class, so let's start our indices at 0. Because computers always start indices at 0. And so this is what the computer is going to do, and then it's going to run a for loop over those numbers. How do you feel about that, 1 to 5? Okay, there it is. So how do we feel about the fact that that's what the computer's going to do? It's just going to assign numbers to this thing and then do a for loop. Right? Odd, closed loop, however you want to write that. All right, so that's how the computer loops over this thing. Okay. Now, we call a set. So what do we use as our indices? We use the set We use the set n to create our indices, and I know I'm out. All right. So I call a set finite, or at most countable. Right? So another way of saying that I call a set finite is that if I can make this thing mapping, right, with some maximum in, I'm good, right? If there's some subset of this where I've got a maximal value, right, the set in, or then little n, then I've got my mapping, right? So if I can use all of the numbers 1, 2, 3, 4, 5, and I stop at 767, I call that a finite set. All right. Now that's a silly way of doing this, right? But that's kind of what we're saying. Oh, it's finite, right? It has a size. Now, what I'm now saying is that the set is finite if I only need so many ints. How do we feel about that? 1 to 5. Now, the next bit is going to be a little tricky. Okay? I call a set countable Okay? I call a set countable if I don't stop at a particular end, but I can make a mapping that includes an indexing that includes every member of the set. Okay? Now that's a weird definition. Okay? In other words, okay. Okay? I've got a number one-to-one relation, a number one-to-one correspondence from the natural numbers to A. In other words, I can put indices on every number. If you give me an arbitrary number, I can find you an index eventually. In other words, for certain problems, this is the best you're going to get. And a lot of times it's good enough. You know that the problem is over an infinite set, but you know that you're after something finite. So you can actually write an algorithm to give you an answer. All right. Now, you don't know how many steps that algorithm is going to take to get there, but it will get there as long as your question is a specific number. Let me give you an example, okay? And you can think about this as I can list them in some sort of order, okay? So let's start with a mapping of the integers, okay? So Michael's got another example. The evens can be mapped, right? 0 can be mapped to 0. 2 can be indices by 1, etc., etc. But let's look at the integers, okay? How can we map the integers? Right? The integers are an infinite set, but it goes off to infinity in both directions, okay? This is the set z equals, how can I index the integers? Z equals negative, dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. I go forever in both directions. Okay. And the trick is to pick a base point for this one. Okay? So, I'm going to start with 0. And here's how I'm going to enumerate this set. And 0 is going to map to 0. 1 maps to 1. And I need to pick up -1, right? So 2 is going to map to -1. 3 is going to map to 2. And 4 is going to map to -2. The fifth integer is going to be sixth, whatever, depends how you count them, is going to be 3. And integer 6, the 6 mapping 6 is going to map to -3. In other words, the sequence is going to be Sn equals 0 maps to 0, 1 maps to 1, 3 maps to 2, 5 maps to 3. N over 2 minus 1 if n is even. Is that going to do it for me? No, 3 maps to 2. Sorry, n over 2 plus 1 if n is odd. 3 maps to 2, 5 maps to 3. So that means I need 6, n minus 1, and plus 1 over 2. N plus 1. So I want 3 to map to 4. Yeah, so n plus 1. Sorry, you can't see me work this out. N plus 1 over 2. If n is odd. And negative n over 2 if n is even. Fun! Okay. How do we feel about that 1 to 5? Michael's typing something, so he's correcting me, so I'll put in the full. Oh, Michael got it already. So this means here, the idea here is that I can list them, right? There's an order that I can list the integers. I could run a loop over the integers by assigning these numbers to them and using this formula, okay? I could run a for loop over the natural numbers and have them assigned to an integer. Okay? Yes, that's negative n over 2. Okay? And that's the idea behind this thing. Okay? If I wanted to, I could write a for loop that would do it for me. All right. Okay. Now, what about the rational numbers? How could I make a mapping of those? Could I write an algorithm that would do a mapping for me? Let's do one. What's the thing about the rational numbers, right? If between any two rational numbers, I can find another rational number. Is everyone on board with that? The natural numbers are what we call, rational numbers are called dense. So what about the rational numbers? Okay, these are dense. Remember that Q equals P over Q, where let's do the positive rational numbers, where P and Q are posits. Remember, we did that huge brouhaha thing about the square root of 2 being irrational. Okay. This would be Q plus, because we're only doing the positive ones. So how can I make a mapping of Q plus? This symbol right here is a Q with a plus sign above it. Okay. If you want it typed, it looks like this. I can't do typing on this program, can't I? If I want it typed, it would look something like this. Insert equation. Where'd it go? Typed, it looks like that. That's this Q thing. Okay. And Q equals the set. Where P and Q are posits. I don't know why it decided to do those as non-italicized. That's annoying, but they should be. So that's what it looks like typed. There we go. Give it a moment to refresh. Yeah. And yes, Q looks like the eye of Sauron. There we go. That's what that set looks like. So the question is, how can I create an ordering for this set, right? Because I've got something big, right? I've got something weird. If I do, is there a number between 1/2 and 1/3? Is there a rational number between 1/2 and 1/3? Right? Problem. So the question is, what number is between uh, uh, 1/2 and 1/3? So what would be an example? Something that's bigger than half, something that's smaller than a half a pizza, but bigger than 1/3 of a pizza. I've lost everyone, haven't I? Hmm. 5/6. There we go. Is that between a half and 1/3? Not quite, but close. 5/6. What about 3/8? Is 3/8 between a half and 1/3? Da, 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 da. Okay. So there are numbers between these, right? Yeah. So there are numbers between 1/2 and 1/3. 0.4 is a perfectly good example. And these numbers are dense. There's always two numbers between anything, any whole number, any two rational numbers. So if I wanted to list them, how would I do it? There are a couple ways, but this is the classic example. Okay? Classic way to do it. I'm going to start with 1/1. Let's stop here. Okay? And what I'm going to do, oops, I need another one of these. 1, 2, 3, 4, 5, 6. Okay. And what I'm going to do is I'm going to say, okay, this is the number 1/1. This is the number 2/1. This is the number 3/1. This is the number 4/1. This is the number 5/1. This is the number 6/1. This here is the number 1/2. This is 1/3. This is 1/4. This is 1/5. This is 1/6. This here is 2/2. This here is 2/3. This here is 2/4. This here is 3/2. This here is 4/2. This here is 5/2. This here is 6/2. All right, and so on and so on and so forth. I'm going to make a big list, and I don't have to go to infinity. Well, I do have to go to infinity, but I don't have to go to infinity in two directions, and I'll show you why in a minute. How do we feel 1 to 5 about this list I just drew? And it's important to know that this list goes infinity in every direction. Okay? Now, here's what I'm going to do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm just going to work across diagonal. Okay? So, S0 equals 1 over 1. S1 equals 1 over 2. S2 equals 2 over 1. S3 equals 1 over 3. S4 equals 2 over 2. S5 equals 3 over 1. I'm sorry, I'm doing them backwards, aren't I? It should be 2 over 1. 2 over 1. This is 1 over 2. This is 3 over 1. This is 2 over 2. This is 1 over 3. And et cetera, and et cetera, and et cetera. And that's the classic way to do it. Okay? And the idea, the big idea behind this is that I form the indices Michael just put it in. I form the indices along the diagonals. And that's the big idea. Back, move you back. How do we feel about that, 1 to 5? Now, I'm going to get duplicates, but I can deal with duplicates. I can toss the duplicates. Once I have my sequence, I toss my duplicates. And I can do that. S3 was 3 over 1, right? 0, 1, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, et cetera, et cetera, et cetera. Okay? So once I have I'll have duplicates, but I can toss those. I can deal with duplicates. Okay? But that's this idea of ordering these things. I can do it. Okay? And I call such a set countable. So the conclusion, and this is actually a theorem, right? Conclusion. Duplicates. So 3 over 3 equals 1 over 1. Okay? Example of those. Okay? So this is a proof. This is actually a proof that the positive integers, this is a proof that the positive rational numbers are countable. And let me find the where that was for. That's the quotient remainder theorem. I don't care. That's the well ordering principle. I don't remember where it is. I thought I saw it somewhere in here. That's why I decided to cover it. I thought it was in 5.6, where they did full recursion. No, I'm sorry. It's in 7.3. So this is 7.3. This is 7.4. Countable sets. There it is. It's on page 478 on section 7.4. Okay. So, a countable, that's a good question. So there's a question about if something's countable. Okay? There are uncountable sets, and we'll get to those next time. The reals, yes, okay, Michael's got it. The reals are uncountable. So there exist sets that are countable, and that just means that I can make this type of list. Okay? It's an infinite list, but it's countable, and that's weird, right? Oh, what countable? You mean that I can stop counting? No. You count forever, but you can count. Okay? You count forever, but you can count. Okay? That's different than a set where you actually can't do this. And there are those existence of the sets. And the way we get there is something called diagonalization. And the thing that we do, and if you want to preview, what we're going to be doing next time is 7.42, is this Cantor's theorem about uncountability of the real numbers. Okay? Are there any questions about this? 1 to 5, how do we feel about this presentation? Right? How do we feel about this definition? Something is countable, and if I can make this type of list. Okay. All right, so I'll put this back here. So the positive rational numbers are countable. And all of this was in section 7.4. Okay. We did sums. Out of time. So I'll pull it back down in just a minute. We did series here and summation notation. We did sequencing sets. This is set enumeration. This is 5.4 and 7.4. And 7.4 is where this material is. Okay. All right. Oops. What'd I do? I clicked something. Okay, there we go. Okay. Next time, we will show that the real numbers are not countable. All right. Any questions, comments, issues, suggestions, thoughts? And this is weird, right? In essence, there's the same number of items in the integers than there is in the natural numbers, even though there are elements of the integers that are not included in the natural numbers. Essentially, the same infinity. Any other questions? Comments, issues, suggestions, thoughts? Okay. If that's the case, I'm going to stop streaming. My time's up anyway. And I will answer any questions that you have in audio chat on Discord. Same bat time, same bat channel on Monday next time.